Châtelier's principle, lecture number 21. So we're going to finish up this first section about equilibrium, talking about the changes that go if we change the conditions from equilibrium. So we add some sort of outside influence that takes our system away from equilibrium, how it's going to shift to reestablish equilibrium. This process is referred to as Châtelier's principle, or however you actually say that in French. Right? So this principle states that if an external stress is applied to a system at equilibrium, the system will adjust in such a way that that stress is partially offset as the system reaches a new equilibrium position. So let's take an example of that. We have N2 plus 3H2 gases are in equilibrium with 2NH3. That's you behind me here. Right? So if we go and add some NH3 to this system as shown in this figure, right, all of a sudden we are at equilibrium, we have a new introduction of some additional NH3. The system is going to switch then. Now we're no longer at equilibrium, we have a Q value, and it's going to shift in such a way that some of that mass is going to be converted back to reactants. So it's going to reestablish equilibrium, changing the concentrations, still following this equilibrium constant so that we get a new set of equilibrium concentrations existing. Right? So in these, we're always going to shift away from an addition. Right? So if we add a reactant, it's going to shift some of that mass to products. If we add a product, it's going to shift that mass back to reactants. Or we're going to shift towards a loss. So if we take some of the reactants away, we're going to see the equilibrium shift to refill that void. If we take some of the products away, we're going to shift that equilibrium towards that. Remember, in this case, I like to think of it as a teeter-totter. We want a nice, stable, flat teeter-totter. So if we're adding mass to this side in order to get it back to stable, we're going to shift in that direction. If we take some of this mass away, now this one gets higher, we're going to shift to reestablish that equilibrium. Right? This teeter-totter analogy works really well. Right? So just again, sort of summarize this. If we increase the concentration of products, we're going to shift to the left. If we decrease the concentration of products, we're going to shift to the right. Increase the concentration of reactants, we also shift right. Decrease the concentration of reactants, we shift left. So we're always shifting some of that mass to reestablish this equilibrium constant, this relationship of the equilibrium constant, and to equalize our system. Right? So the teeter-totter analogy works well. Right? So we can not only change concentrations, but we can change other conditions which is going to affect our equilibrium as well. For example, if we have gases, if we change the pressure, that is going to change. Remember from the gas chapter, changing the pressure changes conditions, right? Because the ideal gas law. So if we change the pressure or the volume, since those are directly related, indirectly related, one goes up, the other has to go down, then we're going to get to see this. And this is going to affect only those gas moles, or those species that are in a gas. So by increasing the pressure, we're going to see that we're going to shift to the side with the fewest number, or increasing the pressure, we're squeezing those together. That's going to cause the system to try to reduce the number of particles that are in the gas phase, right? To give each gas molecule more room. So it's going to shift to the side of the reaction that has fewer moles of gas. If we decrease the pressure, now we have a large amount of space for those molecules, we're going to see that it's going to shift in the opposite way. It's going to shift to the side with the most moles of gas because those molecules now have a whole bunch of space. If we increase the volume, again, that's going to be related to decreasing the pressure, which means that we're going to shift to the side with the most moles of gas as well. If we decrease the volume, right, sort of squeezing those down, it's going to be the same as increasing the pressure, so we're going to shift to the side with the fewest moles of gas. So this pressure or volume, we're always going to shift to the side with the gas. If we have no gas, then changing our volume or changing our pressure is going to have no effect on our equilibrium state. If we have the same number of moles of gas on each side, the stoichiometric numbers are the same, again, we're going to have no effect changing these. Only if there's a different number of moles on each side is this going to have an effect. Another condition that we can change is the temperature. And we've said several times now that these equilibrium expressions are always related to a specific equilibrium reaction and at a specific temperature. So if we change the temperature, not only is the equilibrium position going to shift, but it's going to shift because this relationship, this value of K, is changing. So in the concentration and the pressure, the constant wasn't changing, we were just shifting to readjust to that new conditions. When we change temperature, now our constant itself is changing, which is going to force our equilibrium to change. So the direction it shifts is going to be, the change is going to be directly related to whether this is an endothermic or exothermic reaction. So if we increase the temperature for an exothermic reaction, K is going to decrease. Remember, when we talk about endothermic versus exothermic, we can treat heat as either a reactant or a product. An exothermic reaction, that is a product. So if we're increasing the temperature, increasing the amount of heat, we would essentially be increasing the amount of product. So we're going to see that we're going to cause K to decrease. We're going to shift away from that increase. In an endothermic reaction, that value is now a reactant. So we increase the reactant, K is going to increase. We're going to have more products formed. It's conversely shown here with temperature. If K increases, if we decrease temperature in an exothermic reaction, K is going to increase. Decreasing temperature for an endothermic reaction, K is going to decrease. So not only are we going to see a change in our equilibrium position, but that equilibrium position, remember, is occurring because the K value, this constant value, is changing. Right? So this is, the temperature is the only thing that it's going to affect for that single reaction, the value of K, because of the enthalpy relationship. Right? And we can track these using the von Hofft equation, which we've seen before. The natural log of the equilibrium constant K2 divided by the equilibrium constant K1 is equal to a negative delta H over R times 1 over T2 minus 1 over T1. Again, we showed this one when we were talking about some of the gas properties, but coming back here when we're talking about this capital K. So this is the equilibrium expression. Right? The other thing we can do to affect our reaction is add a catalyst. Right? If we're talking, remember what a catalyst does. A catalyst is going to change the way the steps that the process goes as it goes from reactants to product. It doesn't necessarily change what those two are. So because it's not changing the reactants or the products, changing the addition of the catalyst is going to not change our equilibrium expression at all. K is going to remain the same. And we're going to get no shift in equilibrium. But the thing that's going to happen is, remember, it's lowering the activation energy, which is make the reaction go faster, so we will arrive at equilibrium much quicker in the presence of a catalyst than if it wasn't there. Right? So this catalyst, while it's going to affect the little k, it doesn't affect our capital K, our equilibrium constant. So if we review here the types of stresses we can have, change in concentration, it is going to shift the equilibrium, but reestablish that equilibrium based on that equilibrium constant because it's not changing. Pressure and volume, also when those change, we could see a change in the equilibrium position if we have gas present, or if the number of moles of gas is different from the reactants to the products. But the equilibrium constant is not changing. Temperature, we do see a shift in equilibrium in all cases because the equilibrium constant is changing. Right? And a catalyst is going to have no effect on our overall system.